So today we're going to talk about something called bitwise operations or bitwise operators, which will perform the operations. Um, this is going to revolve around the concept of bits and bytes in a computer, which many of you might be a bit familiar with this already. That's an unfortunate choice of words, or maybe the perfect choice of words, whichever. So if we think about the essential data of a computer, they deal in bits or binary digits, right? So a binary digit can have a value of 0 or 1, and this is different than if we're dealing with decimal numbering systems or decimal digits, where we can have a value of 0 through 9, right, in a base 10 system. And so a byte in a computer is made up of 8 bits. Typically, this is not universally true of all computers everywhere, but I think the vast majority of modern computing systems, 8 bits is 1 byte. Exceptions can and do exist throughout the world and throughout computing, but 8 is a pretty common number. And so the data types that we use are just made up of multiple bytes, especially when we're talking about the various kinds of primitives, right? So we have something like a character or an unsigned character, and that's 1 byte or 8 bits. And we could even describe that as an 8-bit integer, because everything is either some sort of integral type, a whole number essentially, or a floating point type. And so we could have something like a short, which is 2 bytes or a 16-bit integer. And then what we think of as an integer, is really a 4-byte variable or a 32-bit integer. And so we might often, write these things as different data types, which can be helpful from a human perspective. Oh, that's a character. Oh, that's a float. That's a short. That's an int. But as far as the computer is concerned, this is an 8-bit integer. This is a 16-bit integer. This is a 32-bit integer, because it's all just numbers to the computer. And calling them different things doesn't necessarily matter so much. And we can even do this in C++. We can, the data types exist. We could make an int 16 or an int 32 to be very explicit. I want a 4-byte integer. Whereas if we use the data types that we've talked about, int, character, short, or whatever, those are defined in kind of strange ways in the C++ standard. They're defined as things like an integer is at least as large as a short, which is kind of a weird way to say that. Like, so how many bytes is an integer? Well, it's at least as many as a short. Well, how many is a short? Well, a short is at least as large as, okay. And then you really have to get into platform specifics to kind of iron that out, or nail that down, rather, to use that. I think that's a more appropriate metaphor. So if we define something, though, if we write a variable that's like int 32, there are no questions. That is a 32-bit integer. It's not at least as large as whatever. But for the most part, when we're writing these things, especially if we're sticking on one platform, then we don't have to be too concerned with all that kind of stuff, because that's a lot of like cross-platform specifics that can be very challenging to keep track of all those. But we have other stuff to get to, and that's a whole other kind of side topic that we're not really going to get into, right? And so when we think about calculating values of whatever sort of numbering system we're using, let's start with base 10, because that's typically the easiest one, as that's something that we've all pretty much used our whole lives. But if we are dealing with decimal, the place values that we have are based on powers of 10, right? So we have the ones place, the tens place, the hundreds place, and so on. If we had a decimal value of this, 8,935, then we would have something like, or we could kind of break all this down like this, where we have the thousands place, hundreds place, tens, ones, and so on. And so this is really 8 times 1,000 plus 9 times 100 plus 10 times 30 plus, or 10 times 3 rather, plus 1 times 5. And so we add all those up together. That gives us our final value of 8,935, right? And so that's all fine and good. Most of the time, we don't have to think of numbers like this, but kind of formally, that's how they're actually, working out, right? And so if we switch over to a binary numbering system, it's the same concept. We're just dealing with power of 2 values as opposed to power of 10 values. So if I had a binary value written out as 1011, then this is the 8th place for the furthest left digit here, and then the 4 place and the 2 place and the 1 place. So 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. This will give us a final decimal value of 11 in this particular case, right? So we will often take numbering systems and translate them into decimal as we're trying to make sense of them, because that's just often the easiest way to describe these kinds of numbers. Especially as binary values get larger, the number of binary digits increase. It can be very difficult to describe a number when it's 1 0 0 1 1 1 0 0 1 0 and so on. If we're talking about a 32-bit variable, that's a whole lot of ones and zeros, when it might be easier to say, oh, that's the value of 1,506,000, instead of all of the ones and zeros that it works out to be. Okay, so if we do a comparison of these things, we go 1, then 2, then 4, then 8, then 16, 32, 64, 128, and we can keep on doing that endlessly as long as we really choose to, until our patience or sanity wears thin, and then call it done, right? So if we were to take this number and represent this in decimal, then it would be the number, right? So if we took something like this with a 1 in all of these places, then that would be 11,111,000, et cetera, right? If we took that same thing and represented this in binary, however, this would be the value of 255. So now we have, 128 plus 64 plus 32 plus 16, etc. Right? So, okay, that's all fine and good. We don't need to, continue doing this too much. This is just kind of background to make sure that you're all sort of on the same page. We could certainly talk about this a little bit more, give some additional examples and so on, but I think that would be sufficient. But the overall process, though, finding a final value for all this is adding up the products of each place and its corresponding digit. So if we happen to have a 0 in the 64 place, then the product 64 times 0, that's how much that contributes to our final value. If it was a 1, however, then it contributes a 64. And this is true no matter what kind of numbering system we're using. If we're talking about a base 6 system, a base 12 system, or any kind of numbering system, the overall process is the same. But we're mostly going to be focusing on binary and how we can also manipulate these values using these bitwise operations, right? So there may be times when, well, or generally speaking, I'm getting ahead of myself, we modify bits indirectly all the time. All of the code that we write ultimately turns into bit-based operations. If I write this line of code here to say x equals 5, what this is really turning into is a set of instructions that says something like, let's set the bits of this particular memory location to the binary value of 5, which is 0101, with a whole bunch of leading zeros, right? Because an integer is a 32-bit value, so we're going to end up with a tremendous number of bits in that particular situation. I mean, 32 is not that tremendous, I suppose. But if we're writing it all out by hand, it can seem like quite a bit. But whether we actually think about this or not, this is what happens, right? Pretty much every computational process ends up as something like this, right? And we are ultimately doing these kinds of operations, right? We are going to a particular memory address and checking if its bits are equal to something, or we're going to a memory location and setting the bits to something. That's basically it. That's all of computing in a nutshell, right? This is not the most exciting way of thinking about computing, right? It might be much better to, think about the cool stuff that we can do with computers and computing applications, right? If we're talking about 3D rendering or game development or, video editing or any sort of stuff like that, that might be a lot more exciting to describe rather than, well, yeah, go to this memory location, change a couple of bits. Yeah, okay, I suppose that's a thing that you could do, but all of that is happening even if we're doing something more sophisticated, complex 3D rendering or whatever else. It's just changing different bits in different locations, different patterns, groups of bits to represent something, right? So that's generally what everything is in computing. Now, how do we modify these bits directly, though? Because doing it indirectly, this is what happens when we write higher level programming languages. They get translated into lower level instructions, to machine instructions. And sometimes, though, we might want to get a little bit more control over something, right? And so we can do this with what are called bitwise operators. And these allow us to modify bits directly. Now, there's a bunch of bitwise operators, and we've looked at, well, we've seen things that kind of look like these before, although they haven't exactly been the bitwise operators. We've seen, the pipe symbol before. We've talked about this as a delimiter. You've certainly used this with a logical OR operation. Likewise with AND, you've seen this with a logical AND operation, right? If this is true and this other thing is true. Same thing with OR. So it's easy to get those two confused. They have the same name, they use the same symbol. One of them just uses more of the symbol than another. But we also have something called XOR or exclusive OR, something called negation, which is the tilde. It's the same operator or character that we use for destructors. And then we also have something called left and right shift. And these are used, or they are the same symbols as the insertion or extraction operators for cout and cin. All right. So let's start off with OR. And the reason we're starting off with this is perhaps the more common one, or at least in my experience, this has been the most common one that I've ever used. Your mileage may vary with some of these. Some operators are used a lot more in some contexts. It depends. So what OR is going to do is we use this to essentially turn bits on in a value. And so the OR operator is going to compare values, and if either of the bits or either of the bits that are being compared are 1, then the final result is 1. This is very similar to the idea of the OR logical operator, right? If condition 1 is true or condition 2 is true, the whole operation is true. Right? And so if I have value 1, and let's say I assign this a value of 3, value 2 has a value of 10. And so the binary representation of those would be this right here, 0, 0, 1, 1 for 3 and 1, 0, 1, 0 for 10. Because remember, this is the 8's place, the 4, the 2, and the 1 place. And so if I combine these two together using the OR operator, then it's going to check every bit of these values or each pair of bits. And if one of them is 1, the final result is 1. So for this first one, we'll use a 1. For this second one, neither of them is turned on, so we won't have that final results will be a 0. In this third bit here, both of them are turned on, which is perfectly fine, and that'll give us a 1 for the final bit there. And for the last bit, we'll have a 1 for that as well, because at least one of those is turned on, right? So OR is the sort of turn on operation, turn on a particular bit, right? If at least one of them is active or on, then the result will be on. And so the final result of all of this, if we write this out here, is going to be a value of 11, right? So it's not like we're actually adding things, because what this is doing is combining bits, but not adding values, right? So if we were adding 3 and 10, of course, we would get 13. But if we're using the OR operation to combine these together, then that would give us a value of 11, right? Because we're really only getting this one additional bit in this particular case, right? Now, another operation that we can use is the AND operator. So with AND, if both bits are 1, the final result will be 1. If not, then the final result will be 0. So both bits have to be turned on in order to get a final result of 1. So we take those same numbers, 3 and 10, and we go through one pair of bits at a time. For the first one, the result is going to be a 0 because we need both of these to be a 1 to have a 1 for the final result. So we'll have a 0, we'll have another 0 for this next pair of bits. We'll get a 1 for the next pair of bits because both of them are turned on. And then for the last one, we'll get a 0 because only one of them is turned on. All right. So the AND operator can be a good way of checking if a particular bit is turned on. And so this can be a very helpful thing, as we'll see a little bit later on when we look at something called bit fields. So the final result of all of this, if we were to AND both of these together, it would just be a result of 2, right? Because the only bit that's turned on in this final result is the 2-bit. So if we were trying to check if that particular bit were turned on, we can take our initial value and it with the thing that we're checking for the 2-bit. And then if the result of all of that happens to be 2, well then okay, that bit was turned on, regardless of whatever else is happening, regardless of whatever the state of all of the other bits happens to be. We only are caring about that one particular bit. Doesn't matter if any of the others are 0 or 1, because we're only here looking at this 2-bit. Right? So we did this with a bunch of different examples here. We're only looking at that 2-bit right there. Doesn't matter what any of the other things happens or other bits happen to be set to. Okay. Now, another kind of operation is something called the XOR operator or the exclusive OR. So this is one where the operators have to or the bits rather, have to be sort of inverted, right? If exactly one of the 2 bits is set to 1, then the final result is going to be a 1. Otherwise, everything is a 0. So if both are a 0, it's 0. If both are 1, it's 0. If only one or the other is a 1, the final result will be a 1. And so, here, if we go through the same process again, we'll get a 1 for that first pair of bits. We'll get a 0 for that next pair because they're both 0. We'll get a 0 for the next pair because they're both 1. And then we'll get a 1 for that last pair because only one of them is turned on. All right. So XOR is something that has uses in some cases, like, XOR is kind of fundamental to computing, but this is sort of on a very basic level of a computer, like built into hardware. XOR is an important operation on a fundamental level of computing. From a higher level perspective, using this yourself as a programmer, you might in some situations. In my own experience, I've used this very little. It has some uses in things like encryption or security, but aside from situations like that, you may not use this one as much. The OR you may use very frequently, and maybe a little bit less so. XOR maybe a little bit less even. Oh, sorry, that's actually a copied and pasted bit from a previous slide. That doesn't need to be in there at all. There we go. Sorry about that. All right, like I said, this is the first time I've actually delivered this set of slides, so there may be some slight bugs. And by bugs, I mean typos or small little edits that need to be made. I wouldn't necessarily call those bugs. Maybe. I mean, if you program long enough, everything that goes wrong anywhere in any context, it's all a bug. Have a small grammar error in a sentence you wrote in an essay, it's a bug. Yeah, I got to fix some bugs in my essay. What? Bugs? What do you mean, say all of your non-programmer friends, right? So another kind of operation that we can do is the negation operator. And this is a single operand operator or an unary operator where we only have one thing, one operand that comes along with this, right? So it's not like the addition operator where we can have A plus B. An unary operator only has one thing that it operates on. But what this does is it inverts the bits of some value. So zeros become ones, ones become zeros, and that's it, right? Blake, I'm so sorry. I'm so sorry. That's really all I have to say about that. So if we were to use this on the variable new value, we might set this equal to, the negation of some other value. So whatever some value happens to have, all of the bits of that will be inverted for this operation, and then new value is set to those, right? We could do something like this as well. Some number is equal to the negation of 45. So what would all the bits look like for the number 45? Now let's invert all of those, and some number has all of those stored. So if I had something like this, a value set to 12, its bits would be 1100. If I negated that, then I would get the value of 3, which the negation is not always intuitive because, going from 12 to 3, right? Flipping the bits of the number 12, that might not be the most intuitive thing. You might think, well, the inverse of 12 is negative 12, possibly, but negative numbers, that's a whole other thing. What in binary and dealing with bits, there's something called a sign bit that changes the way things get calculated. So it's not really as intuitive of a calculation. But if we just kind of work this out sort of on paper, then we can get a pretty easy calculation of this. And so, yes, if we had a whole bunch of leading zeros for this, it would invert all of those as well. So really, if this value variable was an integer that had 32 bits and only these two were turned on, then I would have a whole bunch of zeros turning into a whole bunch of ones. So, that's a relatively straightforward concept, though, just inverting the bits. There could be some additional nuances that we might run into if we're dealing with certain kinds of values, signed versus unsigned, and so on. But as a concept, just inverting the bits, that's really all it is. And then we can come up to something called bit shifting. So bit shifting is a way of adjusting the bits or moving the bits in a particular value. And the operators that we use to do this are the double less than, double greater than, double angle brackets symbols that we've used for cout and cin up until this point. So what this is going to do is, let's say I start off with a value of 1, which is the binary representation of 1. If I'm just using 4 digits in this case, imagine a whole bunch of leading zeros here, but it would just be 0, 0, 0, 1. So if I were to shift this by a value of 2, or shift this 2 places, then that's going to take the 1 and move it over twice. And so now the new value that I get here is 4. So shifting over by left shifting by 2 is the equivalent of multiplying by 4. If we do another shift of 1, and notice how here we can use shift equals, or we could do equals the original value shifted with 2. This is the same as plus equals, minus equals, times equals, divide equals. All of our arithmetic operators, we can use them as sort of this compound operation. So if I do another shift of 1, then I'm going to move this 1 over an additional place, so it'll go from the 4 place to the 8 place. And when I shift by 1, it's like I'm multiplying by 2 as opposed to multiplying by 4. So anytime we do this shift, it's the equivalent of multiplying by 2 to some power, right? If we if we shift by 2, it's multiplying by 2 to the second power, or 2 squared. If I shift by 2 to the 5th, then, or shift by 5 rather, then it's multiplying by 2 to the 5th power, which is multiplying by 32, right? So The flip side of this, the reverse of a left shift, is a right shift. And it will have the same sort of process. It's just dividing by 2 to the power of whatever. So let's say I start off with a value of 200. And if I write all this out in binary, this would be the representation of the value 200. And so if I do a right shift of 3, that's going to move all of these bits 3 spaces over. And so the new decimal representation of this is going to be the value of 25, because dividing or right shifting by 3 is the same as dividing by 2 to the third power, which is 8. 200 divided by 8 gives us a value of 25. If I do this again, if I shift one more time, then all of the bits will move over 1 space, and the new representation here is going to be 12, right? As we look at these bits, that ends up being 12. And so if we think about this mathematically, 25 divided by 2 is definitely not 12. 25 divided by 2 is 12.5, right? But in this particular case, since we're just dealing with integers, we're dealing with this in binary, dealing with fractions, fractional values, floating point values in binary is a little bit more difficult, right? And so floating point numbers have a different representation. They have an exponent and mantissa and all this other sort of stuff. So, you know, this could potentially make some things a little bit more difficult. But if we're not concerned with that floating point value, that remainder, then, you know, we're fine. Which, I mean, generally we're dealing with integers. We're not concerned with floating point remainders, except in some, you know, small isolated cases, right? And so if we ever shift to the point where we sort of get new bits, like how do these new bits get filled in or anything like that, we should have zeros for the new bits if we want to think of them like that. Also, if we continually shift, old bits will fall off the value that we're dealing with. So if I were to shift, you know, one more time, or when my number has a value of 25 and I shift by one more place, this one kind of disappears and it's just gone. It's not returned. We don't catch it anywhere. There's really nothing we can do about that. It's just gone. That's just the way this works. So if we shift continually, we'll get to 0, because eventually we'll get some new bits that come in as a 0 and the old ones will all fall off. And if we keep left shifting or right shifting, eventually it doesn't wrap around, we just get 0. Yes, Jacob, if we are left shifting and bits fall off the end, they just vanish. If we continually left shift, the new bits, the zeros will go to the left and to the left, and we'll end up with a 0. Right shift enough, left shift enough, you end up with zeros. Okay, so something else that we can do, well, yeah, I see. That's an interesting follow-up question, right? So what does that do to the math? Technically speaking, it is still multiplying by, it's multiplying by 2 to the power of whatever, as long as you still have space to store those bits. If we don't have space to store those, well, then they just get lost. So, right, I suppose you could put a little bit of an asterisk at the end of, you know, oh, it multiplies by 2 to the power of whatever, as long as you have space. Likewise, if we're dividing or right shifting rather, it divides by 2 as long as we have enough space to actually store those bits. Otherwise, we may get some slightly different results. So if we, something else, actually, that's a good pause spot. Let's pause right there. Any questions about this? You know, and I'm going kind of quickly through those, through these things here, because there's not a whole lot more to say about them from just a what it is perspective. And today is just kind of a what these things are. We could get into nuances of, okay, what happens in this situation or that situation, and you know, specific examples, of course. But this is more just here's what these things are. Along those lines, though, any questions? Where do you do this shifting right and left? You can just do this in your code like we have right here. Your next lab assignment, Lab 8, has an example of this. You can use this to effectively store multiple values in a single variable. You could use an integer, for example, and store up to 4 values in a single integer if each of those values is a byte. Because if an int is 1 byte and that 1 byte is made up of 8 bits, we can use bit shifting to sort of retrieve those individual bits that make up these separate bytes of the variable. All of that is explained a little bit more in your next lab assignment. We can also use this if we're dealing with, we could use this as an optimization if we find ourselves multiplying or dividing by power of 2 values. If we can guarantee that the values we're using for some particular purpose are power of 2 values, we can replace multiplication with bit shifting or division with bit shifting, and that can speed things up a little bit. Bit shifting is a much more efficient operation. At least it was in the past. Modern processors may have sort of ruled this out a little bit, but shifting bits is an extremely fast operation because it's not really doing a calculation. Let's say I was multiplying something by 256. If I just multiply it by 256, okay, fine. My computer has code and logic built into it to actually perform that, or my hardware rather has a structure in it to perform that multiplication. Bit shifting, on the other hand, doesn't perform that calculation. It just shifts bits, which is a little bit faster than actually calculating something because it's not really doing a calculation. Right? It's just sort of moving some things. And then the final value is whatever the final value will be based on the new positions of those bits. This is especially important in computer graphics years and years ago when the concept of something called texture mapping first came around. Textures were very slow, and a way to optimize them and to speed things up was to make them power of 2 values for their dimensions. So if an image was 512 by 512, it would be much faster than if it was 500 by 500. Because the number 512, we could do a bit shift based on that, whereas the number 500, we would have to do a multiply. And long story short, we end up doing this kind of calculation hundreds of thousands, if not millions of times every second, and speeding up 100 million operations by a little bit here and there, it adds up. So that goes a little bit beyond the scope of just what we're talking about today, but you might sometimes see these used in situations like that. And a lot of the bitwise operations you may not use in your everyday life. I don't use these all the time, but occasionally. And in those situations, they're useful. Bit fields, for example, this is something that you might find yourself using. And in fact, I used this just the other day when I was working on something for a personal project. And so a bit field is essentially a array of bits. And exactly how many bits kind of depends on what we need. But generally speaking, a bit field is just a collection of bits. Now, we can get a bit field, practically speaking, with our core data types. So an unsigned character, for example, is 1 byte or 8 bits. And so we already have 8 bits just by making a single character. Whether we think about it like that or not, that's what we get. Likewise, if I make an integer, I have 32 bits for free. That's just the way that it is. I don't have to do any additional work to make this 32 value bit field. I just get one, and there we go. So these can be very helpful because we may be in situations where we need to store a whole bunch of values, and I don't necessarily want to have multiple variables to store all of those things. So what I could do is, instead of having 8 individual Booleans or 8 individual characters to represent 8 off or on values, I can just use 1 character and store 8 off or on values in it. So if we take it from that perspective, then the memory usage is going to be a lot better, because if we create something like a Boolean is 1 byte in C++. It represents a true or a false value. However, Booleans are a little bit weird because we could set a Boolean value to a number. I could set a Boolean to 10 or -6 or something strange like that. And the way C++ treats those, 0 is false, everything else is true. Anything not 0 is true. And so that's a little bit weird, but generally we just treat bools as true or false, unless we're dealing with some kind of a buggy situation or whatever else. If I wanted to make 8 of those, that would be 8 bytes worth of data. An unsigned character, on the other hand, or just a regular character, is made up of 8 bits, and 8 bits equals 1 byte. So I've got a fraction of the memory usage, which, don't get me wrong, 1 byte versus 8 bytes, that's trivial. No computer anywhere the world over is really going to be that concerned with 1 byte nowadays. However, what if we do this for a whole bunch of things? What if we do this for dozens or hundreds or thousands of objects in some environment that we're working in, some programming environment? Well, now we might be talking about a real significant amount of data. Not only that, but if I wanted to pass this data around anywhere, I can just pass one single character, and that passes 8 pieces of information, as opposed to having to pass an array of Booleans, possibly a vector of Booleans. If I pass an array by a pointer, that's still going to be 4 bytes worth of data, because pointers are typically 4 bytes. So I'm passing more information. It's not just the raw storage, but maybe passing or copying that data around. That can be a little bit more expensive, right? And so, it all depends on context, right? If we're talking high-end PCs or anything like that, a byte of memory here or there is trivial. Some smaller systems, maybe, but even really cheap, low-powered systems have tons and tons of memory. So we could also use a Boolean variable as a bit field, but that might be a little bit weird. A lot of compilers treat Booleans as very distinct special entities. They can't really upgrade Booleans to numbers and things like that. If we try and compare a number to a Boolean, we'll often get compiler errors, or things might work a little bit strangely. So generally, I would say don't use a bool, at least in C++, as a bit field. So here's something we might do with a bit field. So let's say we had this situation here where we have a character in a video game that can carry a bunch of items, right? So typical, video game stuff, the first-person shooter or whatever. He's got, all these various items that he upgrades over or gets access to over the course of the game. So we have 8 of these things, right? Now, what I could do, if I wanted to keep track of all these things, I could do something like this. Let's store an array of 8 Booleans. I do or don't have each one of these 8 things, right? What I could also do is store these 8 things in a single character. So now in this one character, I have, in this one character variable, I have 8 off or on values. I do or don't have a flashlight. I do or don't have a pistol, and so on and so forth. Now, if I wanted to pick something up with Booleans, I would simply set that particular Boolean to true. If I wanted to pick up the flashlight, then we set item sub 0 to true. If I wanted to pick up a flashlight in a bit field, then I could turn on that bit using the OR operator, so OR equals 1, and that will turn on the 1 bit. If I wanted to pick up a pistol, I set a Boolean to true, or I can turn on the 2-bit, because remember, with binary values, we're increasing by power of 2 values. So 1, then 2, then 4, then 8, and so on. If I wanted to pick up a crowbar, set a Boolean, of course, or I could turn on the 4-bit, right? And so, that would, we need to turn on the 4 value here, the 4-bit, because of our power of 2 values, right? Now, if I wanted to turn on something like a chainsaw, then that would be, again, array sub whatever corresponds to the chainsaw, and set that to true. In the case of the bit field, we would turn on the 64-bit, right? Which really the 6th bit. Now, an alternative to that last option there, we could do something like this. We could do a bit shift. let's start off with the value of 1 and shift it over a number of times to get to the appropriate value. Because if we shift it by 6, then that's multiplying by 2 to the power of 6, which will give us a value of 64, right? So that is a good point, Nicholas, right? The array of Booleans is a bit more user-friendly, perhaps. However, we'll look at a counter to that, ways that we can make our code kind of reverse the user-friendliness of all of this. But oftentimes, code is not so user-friendly. Right? We write code to make our computer do a particular thing, not so much, have instructions that are the easiest to read for a human being. Now, counterpoint to that, it's often helpful to write user-friendly code, programmer-friendly code, human being-friendly code, so we can read it a bit more quickly, right? Depending on what we're working on, though, we might have to write code that is as streamlined and efficient as possible, even if that means it's more difficult for us to understand and more difficult for us to write code like that. So if we let's see here. A quick question. Would bit shifting 1 to 6 not affect the adjacent data? It would, Angel, but only in this case when I'm doing 1 shift 6. The value of 1 is all zeros and just the 1 bit is turned on. So then when I shift all of that over, that turns into 64. And now I'm doing bit items or equals 64. It will not turn on, Anthony, it will not turn on all the previous bits. It will turn on only the bits in the value of 64 that are turned on, which because it's a power of 2 value is only going to be 1 bit. If I had something like 63, that's a whole bunch of bits. And we'll see an example of that in just a second. So now let's say I wanted to drop an item. This is where it starts to get a little bit weird. If I wanted to sort of unequip an item or drop an item, lose something from my inventory, if I was doing this with Booleans, that's pretty straightforward. I can just set a Boolean to false, no big deal. If I wanted to turn something off using a bit field, this is a little bit weird, right? So we look at this and common reaction is some variation on this, like what on earth is happening right here? So turning off a bit is a little bit more involved, right? Because what we have to do is a multi-step process. And so we have an operator. The OR operator is the turn on operator, but we don't have a turn off operator. It just doesn't work out that way. So what we have to do is do a multi-step process. We have to negate something and use the AND operator. So the first thing that we do is negate whatever bits we want to turn off or get the value that is the equivalent of the negation of that. Once we have that, AND it with our original value. And so let's say our binary representation of holding a flashlight in a crowbar is decimal 5, right? The binary representation is 0101, which is decimal 5. And so what I would want to do is if I'm trying to turn off the 4-bit for the crowbar, then I need to take this value and negate it. So the negation of 4, in this case right here, 0100 would be 10. That's where the 4-bit used to be turned on, 11, okay? So this negation right here, we're going to AND with the original value. When we AND this with the original value, for each pair of bits that are both turned on, we will keep that bit turned on in the final result. So combining all these together, if I take my original array or original bit field and AND it with the negation of 4, the result is going to be a 0 for, let me draw this out, note to self, I'll add this for the next iteration of this. So here we get a 0 because we need both of these to be a 1 to keep a 1 in that final spot. For the next column here, only if both of them are turned on will the final result be turned on, which actually that's a small error right there in my own slide. This is going to be a 0 as well, and this will be a 1 because both of those are turned on. Let me correct that real quick. That should be a 0. There we go. Sorry, small copy and paste error when I was making that. So the final result of all of this, the equipment that this person is carrying is only a flashlight. He started off with a flashlight and a crowbar, and now he only has a flashlight. He threw his crowbar at something, dropped it like a klutz, or whatever else. Now, let's say along those lines, we're just about running out of time here. If we wanted to do something like generate a random inventory for our character, we could do something like this, where we run a for loop through this, and we generate 8 random integers between 0 and 1. Let's say if the value is 1, we turn on that particular item. Right? So we do that 8 times, no problem. In the case of a bit field, however, we can just set a random number to our inventory, get a random number between 0 and 255, and that will give us a whole bunch of different pieces of equipment, right? So we might look at this and say, well, how does one random number turn into multiple inventory items? So Alex, not exactly. I don't think you would be able to use this in your project. Possibly because you've got like a tile with 8 neighbors. However, what you really need is pointers to those neighbors. And a bit field isn't going to do that. You need the pointer access to it, so a bit field won't help. A bit field might help if a particular tile is a mine or something like that, but you still need to get access to the thing itself for other reasons, for things like going recursively through all those. So sometimes, yes, you can use bit fields for this. In fact, what I was doing for my own project was a bit field with a 2D or well, it was 3D, but a grid-based environment. And so doing some pathfinding and movement from one grid space to the next using bit fields. But in any case, let's say this random number that we generate is 172. So a value of 172 is going to have this as our binary representation, right? And so that's going to correspond to a whole bunch of different things turned on, right? This 128, that's our rocket launcher. 32, that's our machine gun. 8 is the shotgun, and 4 is the crowbar, right? So random number of 172, we picked up a whole bunch of stuff. Right? And if I was ever checking to see if I had one of those, we can just use the AND operator. So if our array of our bit field rather, and 128 is equal to 128, then that means we have that particular bit turned on, right? So the value of 128 only has a single bit turned on for it, the 128 bit, and so an AND operation with that and anything else will tell me if that other thing has the 128 bit also turned on. All right. Kieran, do you have a question? I saw your hand raised just a second ago.
Yeah, can you hear me?
Yes.
Yeah, okay. So I was just wondering, like to turn a bit off, could you not take the like to turn off like the 4 bit, could you not take the exclusive OR of 4? It's like, since then they would both be on, wouldn't that make it false?
Sorry, the question was, could you take the exclusive OR of what?
Like, sorry, like to turn off the 3rd bit, like, which is, I get value 4, right? Like, could you take the exclusive OR, like, instead of, because you take the OR in order of 4 to turn it on.
Right.
Could you take the exclusive OR to turn it off?
Well, if it was off, you potentially could, yes, because the way exclusive OR works, yeah, you could. Yes. Yeah, you don't have to just use the OR operator to turn something on. Usually that's used as like the turn on operator because it's sort of guaranteed to work. If the 4 happened to already be turned on and you tried to use XOR, it would turn it off. So using OR is kind of a safer operation because if it was already on, it will stay on. But with XOR, if it was already on, it would turn off, which might not be your desired result. And it really kind of depends on context. Right? So could you?
Yeah, well, that's why I was asking, like, if you could use it to turn it off if it was on, like, instead of doing the and if
Oh, I
should.
see. If it was, yeah, you could also do that. Yeah, that could work. Yep. Yeah, I mean, with these kinds of operators, there are a variety of ways that you could use them. There is no one single way to do it. Right. So let's see. We are unfortunately out of time, but I have like one or two more slides. Let me finish this up because we're basically done. But to add to or to sort of bring it back to a little bit user-friendly way, enumerations can sometimes be used to help out with this. So instead of having to remember, okay, this item is the 1, this item is the 2, which item is the 32 again? I don't remember if that's a shotgun or a rocket launcher. Wrong on both counts. It's actually the machine gun is 32 and so on. We might use an enumeration. And so if we wanted to do something like, turning something on, we might do a line of code like this, right? So we could say our items or equals the laser. Okay, now we just picked up a laser. As opposed to or equals 16, because what's the 16? And having to constantly remember all that is not always ideal. So instead, this makes our code a little bit more readable, right? Now we could also take this idea of a bit field and we could wrap this up in a class or something to that effect. And we could have functions to handle some of these things. I could say character dot add to inventory and then pass it this laser value. And internally, it's just using a bit field to represent all of that. Whereas I might have a cleaner outward facing interface, right? Because that outward interface, that's really just a bunch of code instructions that wrap up or kind of hide the true functionality of all this that make it a bit more user-friendly for us. So there are a lot of different bitwise operations that we can use for a bunch of different purposes. Some of these you might use more so than others. Like I said, the OR operator, I use this one a lot. Well, out of all of these operators, I use it a lot. I don't do a ton of bitwise operations, but OR is the one I use the most, followed by and after that, I don't know the last time I really used XOR or negation. Those ones for me personally are used relatively infrequently, but they do have some uses in things like encryption and security. Those are areas a bit out of my realm of expertise, but they are used a bit more frequently there. And writing these kinds of operations is allowing you to manipulate things a little bit closer to the sort of true nature of your computer, a bit more closely to its native language, as opposed to, well, I need to store a number, so I just have to store it in whatever kind of data type is best suited for it, even though you might not need that large of a data type. Even a single byte can store up to 255 as a value, but maybe you only need to store the number 0 through 6. So storing it in 1 byte is maybe a little bit wasteful. If you need to store a tremendous number of those small values, then bit fields or bit manipulation might be a better option. A lot of times this is for optimization purposes, which if we're writing simple programs, we may not be concerned with optimization at all. Because our program is so simple that any kind of modern or even semi-old hardware can process it with no trouble. It all depends on what exactly we're doing, right? Okay. And that is all I got for you guys. Any questions, comments, concerns? Let's see. Blake, do you have a question?
Yeah, I think Jacob was asking about it in the chat. We were wondering if you could use XOR as sort of a toggle if you wanted something like that.
Yeah, you could, because if it was off and you XORed it with something, then it would get turned on, and if you XOR again, it will get turned off. So yeah, absolutely.
Cool. And then about the, what do you even call it? My first thought was NAND gate, right? When you were saying how to turn it off. Is that right? I'm trying to get the order right in my head. Like, sorry, when you're turning up a bit in the bit field operation, right? you're doing and equals not this number. So is that like doing a NAND operation directly, or is the order backwards there? I'm not sure.
Yeah, I think it would. Honestly, my hardware-based operations, possibly. Yes, I would have to, honestly, I'd have to look that up again. It's been a long time since I've looked at that kind of super low-level logic. I tend to, stay much higher on the application level. So I think it is, but I would have to honestly review. And
Gotcha. That's fair. Okay, thank you.
all right. I mean, I don't like to admit, that I don't know something, but that is the truth. Let's see here. Any other questions? Doesn't look like it. Yeah, so that's all I got for you guys. If you are traveling this holiday break, please be careful. Please be safe. Coronavirus is no joke. Definitely not. Several students in this class have gotten coronavirus over the course of the semester. So please be safe out there. Have a good Thanksgiving break. I don't have anything planned as far as anything over the break. No additional material or whatever else. We'll pick up with all this sort of stuff next week. If I do come up with anything, though, I'll make an announcement and post it and get to at your leisure. But nothing is required. So take some time off if you can, and have a good Turkey Day or Tofurkey Day or whatever you might be eating on Thursday. Happy Cheeseburger Day if that's your thing. Whatever. I don't judge. Yeah, so I will see you guys on Monday.